Hi, we are continuing the discussion in chapter 4, and today we'll discuss the basics of pipelining. And let's take a quick introduction to the basics of pipelining so that we are aware of what we are going to discuss. Um, Basically, pipelining is the principle of breaking the tasks between, or the big task between multiple agents. Let's take, for example, when you go to a restaurant and you walk into to the restaurant, right? And here is one employee in the restaurant, and where you can order the food, what you want to order, pay money, and then the same person, the same employee will cook the food and present or deliver the product to the customer. Now, the idea really here, instead of you going to a one person, you notice that the entire process, which consists in this case, for example, for instance, of 4 steps, right, is done by just one person. The better way to do it is to have a counter of 4 employees, right? And there they are, okay? And these 4 employees, right? The customer walks in. So the customer first order the food at this counter. Then the customer moves in, pay the money. Then the customer moves in, and this employee will cook the food, and then this customer finally will package and present the tray of the food. Now, in this case, what I did, I broke this complete task here into 4 steps, where and I had to hire 4 employees, but notice that I'm now can have more customer come in, and every one of them, once the order is given to the first employee, I can receive the customer, the second customer, the third customer, the fourth customer. So it seems to me that this customer per time has improved, and this is what we call the throughput of my process has increased, because what I did, I broke the large task into a smaller tasks, where someone can handle this very a bit in smaller. Okay, so with that, let's go to our lecture here. And here we can see he is given an example of a laundry and how we can break this task into subtasks, and we can improve the process. And I think uh, we, we have a different example for you, so you got the idea. In terms of the MIPS processor, we can identify that the execution of an instruction can be divided into 5 tasks. The first task, or the first stage, it is the instruction fetch, where we fetch the instruction from the memory. So we read the instruction from the instruction memory. Then the second stage, what we do, we decode the instruction and we read the operands from the register file. And the third stage, what we do, we execute the operation in the ALU, okay? Or we probably do the same thing, but we calculate the address. We also need the ALU for that. Okay, in the uh, fourth stage, we access the memory to read the operand, to read the data that we want to load from the memory, or we access it to write the data in case of a store. And the last stage, we write the result. Either this result is coming from the ALU, or the result is coming from the memory in the case of a load instruction. Now notice that I have here how many stages? 1, 2, 3, 4, 5. Therefore, I can identify that this processor has, or I can create a pipeline. Now, once I identify the subtasks or the stages, I can create a pipeline of 5 stages for this processor, where the first stage is instruction fetch, ID, where I decode and register read, execute the instruction, access the memory, and write back. We need to know those very, very well. We will use these acronyms till the end of this chapter. Okay? Now, here, what we want is to see what happens if I execute the instruction, instructions by instructions, like in the case of the example of a restaurant. Let's assume that we want to calculate the time we need per customer without pipelining. Without pipelining. Now, here, if I execute a load, okay, I'm going to assume, by the way, that I need 200 picosecond for instruction set. I need 100 picosecond for decode and register read. And to execute, I need 200 picosecond for the ALU. And to access the memory for read or write, I need 200 picoseconds. And to write data to the registers, I need 100 picosecond. Now, in the case of a load instruction, obviously I need to fetch the instruction, I need to read the base address, and I need to calculate the address to access the memory. I need to read the data from the memory. I need to write a register back to the register file. Add that, we come up with 800 picosecond. In the case of a store, I'm going to do the entire steps except the write back, because basically I'm writing to the memory. There is nothing I'm receiving from the memory. And in this case, I need 700 picosecond for this instruction. In the case of ALU operations, add or subtract, add or nor, etc., I need to fetch the instruction, read the operand, and execute it, and then write the result back. And for that, I need 600. Now, instead of branch if equal, I need to read the instruction. I need to do register read. I need to do the ALU so that I can compare the two registers, and then take the branch. And for that, I need 500 picoseconds. Clearly, I have different times for these instructions. Okay, and for that, if I want to create a pipeline, now this is the non-pipeline. I'm going to call it the scalar processor. So scalar meaning non-pipeline. But if I want to move this into a pipeline processor. Now notice that the pipeline processor consists of these stages, right? 1, 2, 3, 4, 5 stage. Now notice what happens is that this is the very first instruction that I'm executing. Now once I fetch it and I complete fetching it, I go and fetch the next instruction and introduce it to the pipeline. Once I finish fetching the second instruction, I go and fetch the third instruction. In other words, I keep the pipeline busy. But the interesting part here is that every stage in the pipeline will take equal amount to the slowest stage. So you will see that here the slowest the slowest stage in these stages is 200 picosecond, and therefore the pipeline stages, every stage must take 200 picosecond. I cannot make the stages equal to 100 picoseconds, because this means that the data will clobber on each other. So the length of the stage of the pipeline will be equal to the slowest. In the case of the scalar pipeline, I can speed any step because I don't have multiple instructions running in the pipeline. Now, of course, once I move from a scalar implementation to a pipeline implementation, the question comes into mind: what is the speed up? What have I gained from this process? Okay, well, and for that, what we'll do, we will use the CPU time equation that we derived in chapter 1, which is equals to the instruction count times the CPI times the cycle time. Now I can merge the CPI and the cycle time, and I come up with the instruction time. So what's the instruction time? Well, the instruction time equals CPI times cycle time. And this is, I will use it to solve the following example. Well, what about the now? Suppose I have in different times for different instructions. So in this case, I will have to use this formula where every set of or class of instructions, I will have to apply to it or multiply it by its own share of instruction count, and it is its own instruction time, as we will see in the example very shortly. How about the CPU time for the pipeline? Again, we go back to the original formula here, and what do? I merge these two terms to create something I called number of cycles times a cycle. So what's number of cycles? It is instruction time times CPI. For a pipeline, number of cycles equals fill time plus instruction count. And for that, let's go to the whiteboard and take an example for that. Let's say for instance, if we have, for example, this pipeline. Okay, so I'm gonna use this multi-cycle diagram. We'll study it later on, but suppose, for example, I have this multi-cycle diagram. Okay, so I have here the first instruction, the second instruction, the third instruction, the fourth instruction, the fifth instruction, sixth instruction, and seventh instruction, for example. And let's have, for instance, see if I can. Uh, okay, let's have. I need to make a quick grid here. Okay, first instruction, second instruction, and third instruction, and fourth instruction, and fifth instruction, and sixth instruction, and seventh instruction. Okay, now, so now let's check for the first instruction. So this is cycle 1, cycle 2, cycle 3 in terms of cycle. 4, 5, 6, 7, 8, 9, 10, 11. Okay, now let's say in the very first cycle, I'm going to fetch the instruction, and it will go and will process it in the first stage, which is the instruction fetch, right? On the second cycle, the first instruction goes to the second stage, which is instruction decode. But I can also, much like the restaurant example, now I can go to the instruction second instruction and move it to the instruction fetch stage, because the instruction fetch stage, it's not doing anything. Now on the third cycle, I'm going to move the first instruction to the execute stage, okay, and the second instruction to the instruction decode stage, and I can start with the third instruction. Okay. In the fourth instruction, I can move this first instruction to the MIPS stage, okay, and the second instruction to the execute stage, and the third instruction to the ID stage, and I can start with the fourth instruction where I have the instruction fetch. On the fifth cycle, I can have the last stage for the first instruction, which is write back, and a second instruction it go to the MIM stage, okay, and the third instruction can start on the execute stage, and the fourth instruction, it starts on the ID stage, and I can start now the fifth instruction in the instruction fetch. Okay, now for the sixth cycle, this instruction is done now, completed. So the second instruction goes to the write back. The third instruction goes to the MIM stage, and the fourth instruction goes to the EX stage, and the fifth instruction goes to the ID stage, and the sixth instruction goes to the instruction fetch. Okay. Now, in the seventh cycle, so this instruction now is completed. Now, this seventh cycle, I can have the third instruction. The third instruction goes to the write back stage, which is the last stage, and the fifth instruction, okay, so the fourth, the fourth instruction goes to the MIPS stage. Fifth instruction goes to the EX stage, and sixth instruction goes to the ID stage, and the seventh instruction starts the instruction fetch. Okay. Now, so you can see this instruction has completed now. Now, notice here in the eighth cycle, I can have this instruction, which is the fourth, go to the write back stage. Okay. And the fifth instruction goes to the MIPS stage, and the sixth instruction goes to the EX stage. Okay, and the seventh instruction goes to the ID stage. Okay, I don't have anything after the, I don't have eighth instruction, so this instruction is completed and nothing in the pipeline goes in. And now here, now I use the in the ninth instruction, I have the write back for stage for instruction 5, MIPS stage for instruction 6, and EX stage for 7th instruction. And then, so this instruction has completed, which is instruction 5. Instruction now 6 goes to the write back stage in the 10th cycle, and which makes it complete here. Okay, and MIPS stage for the 7th cycle, and in the 10th cycle I go to the 11th cycle write back stage for the 7th instruction. Okay, now what I want to do here is for this pipeline to compute how many cycles I needed. So obviously for me it is clear that number of cycles is 11, but how did I get here? Observe the following, because from here, from this cycle, I am finishing one instruction per cycle. So from cycle 11 all the way to cycle 5, this is how many instructions, how many cycles I have? I have 1, 2, 3, 4, 5, 6, and 7, which is actually equals the instruction count, because I have how many instructions here? I have 7 instructions. So I have 7 instructions here, but I still have this period here of 4 cycles. What is this? This is called the fill time, the time that I need to fill the pipeline. Notice that the pipeline up to this cycle is not full, and it is equal to number of stages minus 1. In my case, how many stages I have? 1, 2, 3, 4, 5 stages. So 5 minus 1 equals 4. So therefore, the number of cycles equals what? Equals a fill cycles, which is 4, plus number of instructions, which is 7, and which is equal to 11 cycles. And this is what I got in the block diagram. Now let's go to our lecture here. So for the CPU time for a pipeline, I need to compute number of cycles times the cycle time. Number of cycles equals the fill time plus the instruction count. The fill time equals number of stages minus 1. So now if I divide the CPU time for the pipeline, I'm sorry, the scalar on the pipeline, okay, it will from the previous slide, it was instruction count times instruction time. Okay, so from the previous slide, the CPU time for the scalar equal instruction count times instruction count times instruction time. Okay, so this is instruction count times instruction time. For the CPU, for the pipeline, it is number of instruction count uh, plus the fill time. So in the maximum value we can get here equals S, which is number of stages. So that's the fastest I can get. That's the best speed up I can get in terms of pipeline processor. So in case of MIPS process that we are studying, that will be 5. Now let's take an example here. Assume I have a program with in instructions. In could be 100, 1,000. 10% of those are loads, 10% of those are stores, 50% of those ALUs, 30% branches. Assume that the stage, assume these timings, right? So the CPU time for a scalar processor equal the time to execute the loads, okay? And how many loads I have? N times zero point 0.1. What's the time a load takes? 800. The time that I need to execute stores, how many of those I have? I have this much. What's the time to execute a single load? It is 700. And the time to execute ALUs, the time to execute branches. Add all that, this comes to N times 600 picosecond. How about the CPU time for the pipeline? Well, we have seen this is the fill time plus number of instructions times cycle time. So the cycle time equal to the slowest of all of these. The slowest of all of these is what? 200 picoseconds. So this is the cycle time, 200 picosecond. Now, I know S minus 1 plus N. S here is 5, and minus 1, this becomes 4 plus N. So what's the speed up? What's the speed up? The time for the scalar over the time over the pipeline, which is equals to if n is very large, I can ignore s, right? So this becomes 600 n over 200, which is approximately a speed up of 3. Now, once you said why 3? Because we predicted just a while ago that the speed up should be number of s. I say yes, number of s, but this is when you have all the stages are equal the same time. But here, since I have stages with different time, I lose some of the speed up because of these errors or inconsistencies. Okay, so this is as much as far as the pipeline. As I said, the pipeline speed up is equal number of stages. Now, the pipeline. The question is what's the time between the instructions between the pipeline? It is the time between the instructions in 9 pipeline divided by number of stages. That being said, for example, if you have equal number of stages, let's say for example we have a number of stages here 5, and it takes 1000 picosecond to execute a single instruction on the scalar. So the time of each stage will be 1000 divided by 5, which is 200 picosecond. That's the length of the stage in the pipeline processor. Okay. Um, Now, for pipelining, it is important to realize that all of this is good without the hazards that attacks the pipeline and slow it down. And we will discuss those hazards in the next lecture. But before we go there to the next lecture, I want to stress on the fact that pipelines they don't have to be just we looked at the processor here, which is 5 stage. In other words, our pipeline, we assume it is 5 stages, which is instruction fetch at the beginning, then decode, then execute, then mem, and then write back. In modern processor, memory sometimes is very slow. So what they do, they divided it in multiple stages. So you will see something like instruction fetch, instruction decode, execute, and then you have mem stage 1, and mem stage 2, and then write back. And in this case you have so this is 5 stage processor, and here you have 6 stage processor. All are valid. So the number of stages that you partition your processor is based on the circumstances and the parameters and the specification of the environment and the design that you are carrying. So, and sometimes some processors they go into 10 stages. Some are deep pipeline; they take 30 stages. Although recent processors they try to avoid such deep pipeline. They call those, by the way, super pipelines. Super pipeline where you have really large number of stages. So the people try to avoid those. So the fact is, uh, the more you break number of stages, you hope that your speed up will increase. So because we've said that the speed up ideally is S. So if you have speed up of pipeline compared to scalar. So if you have 5 stages, your speed up is 6. If you have 6 stages, your speed up is 6. If you have 30 stages, your speed up is 30. Is it correct? Well, not quite so. We will see that there are things called hazards that will slow my pipeline down and will slow down my pipeline, and we'll discuss those in the next lecture. And thank you very much.